this particular problem. So we say that y2 x cubed plus 2x plus 3 mod 5 mod 5, correct? Now we say, okay, what about if x is 0? Well, let's do this. y2 is equal to 0 cubed plus 2 times 0 plus 3 mod 5, right? And we end up with something like this, 3 mod 5. Now the next question is, in order to find out y, right, this is just y squared. But here it says, can we find a number that is divisible by the following number, actually? Let's do that. So what is that we're trying to do here? Has to do with divisibility, right? 5 divides evenly any number y squared minus 3. Remember that formula from the screencast, right? That is all we are asking, right? So what number here, right? What number here we need in order for these numbers to be divisible? So maybe we can try a few, right? Now, the interesting part is that because we are modulus 5, we can reduce the set of possible answers between 0 and 4 values to try in y squared. That's the cool thing, right? Modulus makes things relatively simpler. So let's say if I want to put what number is for 0, right? If it's, let me see, y equals to 0, 1, 2, 3, 4, right? Now, if I do y squared, the rest you cannot see, right? Some of you are not, let me click fully here. I see some of you are not discussing this. Well, the square part of all this would be 0, 1, 4, 9, and 4 times 4, no. What are we doing here? Oh, thank you. Gosh. There you go. And then we have to do -3, right? This is any number, like, that's why I like Haskell, because I can do this in Haskell. Like, apply this, -3, -3. So this, in this case, that would be -3, -2, 1. This is a 9, of course. That is a 7, right? And this guy would be 13.
That's a 6, not a 7.
Ah, thanks. There you go. Hard to focus when you're looking downward. 6. Yes, please. Question somewhere here.
Yeah.
Jeff.
Y squared, 0.14968. How did you get that again? How did you get 916?
Very good question. So I said because y should, so the result of any curve that is mod 5, it doesn't matter how large is the number in the multiplier, it needs to land in the clock, right? Around the clock of mod 5, has to land on 0, 1, 2, 3, or 4.
I see now, you did Y squared.
Yeah, okay, cool. Cool, okay. So that's the clock, right? This is the clock, but then I just need to square it. And then I need to subtract -3. Which one of these suckers, right? It's divided evenly by 5. Do you see any number what is the rule for division by 5 in basic rules of arithmetic? Any number that ends on 0 or 5. Thank you very much. Clever. Is any of those numbers here? No, right? So the whole set has no solution. And that's why you, let me bring here, a little bit lost here. Where's my pointer here? And now it's a graph here. Okay, so I'm gonna stop the recording. I don't know why is it recording? Yeah. So let's switch back here. Trying to remove that one from here. My pointer is not working. Okay, so QuickTime, where's QuickTime? Trying to move from one screen to another and I can't. I mean, cancel it by my computer. Finally. All right. Let me screen up here. There you go. That is why the first line on this set is no solution, right? Now, if I were to repeat the same process for this line, let's see if we can do it on the fly, right? So if we replace x for 1, in that curve, we have 1 plus 2 plus 3. It's like 6 mod 5, correct? But this is y squared. So again, we have to say, hey, which number, y squared minus 6 from the possible values for y, which are 0 to 4, which we're gonna square, are actually divisible by 5. And if you recall the set that I had earlier, right, where I say none of these numbers is divisible evenly by 5, well, for this particular case, 1 and 4 will highlight them, right? They will be highlighted because, yeah, so it will be divisible by mod 5, one of these, right? So remember that, so if I were to say the following, let's see, so we have 1, L to Y 1, 4. Let me think about this. Okay, so the reason is because you're testing y squared with some number 6, right? Y squared 6 mod 5. And what you want is, okay, how do I go from, if y, it turns out to be, let's see, 1 and 4. On the left-hand side, if you had, I guess I can, let's see if we can do the math to explain it a little bit better here. Am I having still recording? Is that recording from, oh, that's the recording from Zoom. That's why I cannot get it out of here. It's not my quiz here. One second. Quick timer. Oh, finally it comes up really quickly here. So let's work this example a little bit further here. So let's go for y. Maybe I can switch a little bit more. Square, and we agree that that is 2 first plus 2x plus 3 mod 5. Now, in this case, we claim x will be 1, hence y squared will be 1 cubed plus 2 times 1 plus 3 mod 5, correct? Now, pressing the issue a little bit further, we say square, y squared, this is just 6 mod, mod 5, correct? Now, if let's assume that earlier, right? Earlier, we can discover it ourselves, but we already saw the answer, right? These guys could be 1 or 4, correct? For y, y could be any one of these. So if I plugged in, right, y with 1 here first, and this 6 mod 5, right? Pretty much this solution is 1, 6 mod 5, which happen to be, if I ask the following question, is 6 minus 1 divisible by 5? It is divisible by 5. Hence, it has to be a solution, right? Evenly divisible, you know. Now, if I do the same thing for 4 square, oops, sorry. We have 6 mod 5, and probably some of you that are faster than Dr. Bravo for the math, you can say, okay, it's 5. Does 5 divide evenly 16 minus 6? Yes. So these two numbers must be the solutions for the points that we're looking for. Remember, we're looking for x and y, x comma y as a point. So this is why we're doing all this mess, right? We're trying to find exactly some numbers that do exist. We already observed that some of the values for x that we picked between 0 and 4, especially x equals 0 in this case, is not a solution. It means like you need to keep going. You need to find x1, x2, when x is 1, when x is 2, when x is 3, and when x is 4, in order to find the points that belong to this particular field. So we find 1. If we keep going, then we can find some more or not that many. Probably some will be similar, no solution, but we'll find at least 2. We're hoping if they give us the right elliptic curve, right? So, I mean, we can use the same elliptic curve and stretch the clock. We can use mod 5, mod 6, mod 7, whatever, right? It could be anything we want, as long as the curve is well defined within that range for at least 2 points, so we can find the third one and so on. All right, so I will stop for a second and ask whether, is there any questions why the numbers here? And let me stop that one. Probably I can expand that one here. Full blown. So now is 1,4. Will you be, can you do one of those, the next one? Do you feel like comfortable following the algebra we just did? It's not super hard, right? So I'm confident that we can find those points really easy in a problem. If you get a problem, especially if I give you some code, then you can just run it, just adapt A, B, and C and the modulus, and a script should be able to give you the solution. But a solution is not work if you don't know how it works, right? So that's why I stopped here to tell you how these numbers are computed. All right, so at the end, so let me remark that one, and let me bring, where's the pointer? Ah, there you go. The laser pointer. Okay, so all these X follow the same pattern that I just did for 2 points. So you should be good. Now, the slide shows that there's a sequence of points right here. So let me tell you, is there any coordinate here where x is 0? No, because we already agreed that x for 0, there is no points, or there are no points. Hence, we see points with coordinates in x 1, 2, 3, and 4, actually, right? And then it follows that for 1, we have 2 points, right? For x equals 1, we have 2 points for y, 1 and 4. So that's why you see 2 points. Then for x equals 2, we have just 1 point, which has a coordinate y at 0, which I can hover over that. And then for x equal to 3, we encounter similar values for as in x equal to 1. And finally, we found that x equal to 4 has a y value. It does mean there's a solution for y for the equation when it's y is equal to 0. Now, this infinity point comes from this guy here. All right, that's how it turns out. Like, yes, there's a solution, but it's called infinite or something like that. So when you see infinite, don't freak out. Like, it just, we have to deal with that. Now, in your book, there's a better way to present this math. Unfortunately, I forgot to take a screenshot, but the math here is the following. We agree that in order to do the cryptographic encoding of cryptographic process, we want to compute a third point, right? A third point, which is P3. Now, if P3 is the addition of P1 and P2, but not only that, we need to mirror, right? Remember that there's the intersection of a line, and then we have to kind of create a mirror according to the graph we saw earlier. This is the math that is involved in that process, right? To find the intersection of those points in the curve and later mirror that, and then you find P3. So let's take a look at really quickly. I will not spend too much time here. But certainly you can compute this by hand, or you can use any programming language of your liking. So let's take a look at this. We already have 2 points, P1 and P2 from the list earlier, right? We know we had some of those. It means that I can potentially compute x3 by the following. By squaring the slope of those 2 points. Now, again, this is recalling a little bit of your, back in the days math kind of classes. The slope between 2 points is pretty much just the difference between the xy coordinate of one minus the y coordinate of the other over I say earlier y coordinate minus the other y coordinate of the other point over the x values of those points, the difference between those x coordinates of those 2 points, right? Sometimes we call it the delta y over delta x. I guess in physics, we used to use that notation to simplify all this verbosity. I'm trying to explain how that works by hand waving. Now, that is the m, right? Normally, that is m, right? Those delta y over delta x. And if you have those values, they are discrete, right? They are not, by any means, they are fractional. So what you're gonna do is take that value, square it, and then subtract the values of x1 and x2 from the same points. Compute the modulus of that value. In this case, is p, which normally for encryption, we use normally prime numbers. That's why it's a p there. But it's the same n that we have earlier, like number 5, for instance, right? 5 is prime, right? So we can do 5. That value will compute x3 for P3, right? We're looking for coordinates again, correct? Now, there's a caveat here, very simple condition. They say, hey, if your points are different, use this formula to compute m, right? If they are equal, use this other formula. Now, if you ask me, Why is that? That is the very involved theoretical part of the math behind ECC, right? Now, by very simple logic, I said, well, if the points are identical, your slope will end up to be 0, right? Like a flat kind of thing. So this is a mathematical trick to make sure that the slope goes across a third point somewhere there in your graph, right? Probably a slope being zeroed is not bad, right? But it will change the way you cross a third line and then you mirror it. That's all what I can perceive from here. All right, so now what we have here is, all right, if P3 is infinite, then all the P's are infinite for everyone, meaning like if you are dividing by 0, right, or something like that, then these are special cases that you address differently. All right, so these are just the cases where where the points are equal or different, and then the value is square it and use it to compute x3, and finally we use the slope for this. So if you recall, this is just solving for y3 having the same slope, right? M equal to delta y over xy. Well, delta y would be y, kind of 3 minus y1 and so on. Does that make sense? This is just precisely that solving for y sub 3 from the point based on, let's say, 0.1, right? You are computing the slope towards that point P3, but you use not the slope, but you try to find out y3. Any questions so far about this math that looks hard, but I hope we distill it and you feel like comfortable computing this stuff. So finally, y3, right? These two together are our coordinates for the point 3. And that's how much we can compute from elliptic curve maps. Now, what is being said here a lot? So let's say, consider this y, and then consider that these points exist on the curve. Then what is our P3? Then again, this is just a numerical example to compute the curve, right? Like the P3, sorry. Anyone can now do this or any other type of curve. Now, if you use prime numbers, right? If you use modulos that are large, obviously, this is a toy example. But for larger prime numbers, probably you want to use a programming language, right? Just to do it for you, all this computation. You don't want to go by hand. All right, so we have 2, 0, it's P3 on that curve, apparently, and that's about it. So we say that ECC does exist. The kind of the analogy or the correspondent Diffie-Hellman ECC is given in this example. So we say we have an elliptic curve and a point xy on a curve, right? This could be very well P3, right? So we have Alice A and Bob's B. It will be the private key. These are some multipliers, right? So you will see in a second. So what is going to happen is Alice, right? So normally we share public keys. Here it says that multiply the value of a random value picked by Alice, A times the point here. And Bob will compute a similar, right? The point xy times B. If you recall Diffie-Hellman earlier, remember those generators times AB, right? If Trudy detects G to the power of AB, Trudy cannot really factorize, right? Find the factors of AB because they are already computed. Similar thing here happens, right? So here it says, now Alice computes A times B. So that's why is the similarity with Diffie-Hellman here. And Bob will compute the same thing. And now, guess what? These are the same scenes, these two, right? A and B and BI, the order, it doesn't matter, right? it means that at this point, Alice and Bob have shared a common key, correct? So here's an example. A curve. I'm trying to convey you that every time you see this curve, there should not be a reason for you to be intimidated, right? When you walk out of this room, we walk the mat here, you will forget about the mat and say, oh, there's some programs that will help me find those points for me, that's all. But you know that these are just coordinates and there is a methodology to find those points. All right, so the curve is this, there is a modulus 37, we picked a point, and then we select, this yields to the value of B for Alice and Bob choosing these factors. For this particular example, we are picking B to be this value. Normally, actually the example in the textbook says, hey, solve for B. It makes it a little bit harder for you to compute those points because you need to solve for B, giving a point XY, right? But it's not a big deal either. Because we're engineers, awesome, computer science and mathy people. All right, so these two guys, Bob and Alice, picked a random value, A and B. So now Alice sends Bob the values of 4 times this point, right, 2 and 5. And now it's computed here. And Bob will do the same, right? He has its own curve on the other end. And now, so we said that the curve is public, right? Anyone can see the curve. Now, the tricky part is, who knows what these values are that were computed by Bob and Alice, this particular point, correct? Now, again, these points become very complicated to guess which point was picked by Bob or Alice, let's say 2, 5 in this case, because with larger modulus, that's the magic of ECC. It's like it's huge numbers, like you don't even know where this P1, P2 crossing at a tangent or slope line, and then finding the image of that point in a gigantic curve. To find that point and just guess that point will be complicated if you don't have the right values to reverse that. All right, so the multiplications are being sitting here, and we just compute again the factor the multiplier times these points end up to the right hand side. You see every single value being computed. And now Alice computes using the multiplier 4, and Bob should use the multiplier 7 to compute a common value, right? This point is what they share in order to compute and encode message. Now there's a larger value here. Again, like the textbook is just trying to tell you, we are just walking our way with the toy examples, but there are some already well-known curves that are useful for encryption. So now look at these gigantic values, right? P is the modulus, A and B are the coefficients of the polynomial, right? X and B, A and B. And then you say, well, then what? Let's see. Why this lower menu here is, I guess, getting in their way. Okay, so it's not there. All right, so very quickly, the following point P is on the curve, just like earlier it was 2, 5, right? Now we look at this enormous value, right? It's not gonna be easy for anyone to guess this one. Now there will be another multiplier here, K. Now it's as large, right, as these other points. So if we multiply K by those two, we end up with these 2 points. So this is just a very specific curve giving in some standards. Now, this point, according to the math behind it, it says this point does exist also in that curve. So it means that, again, at this point, what it's been said is, okay, so these points will help you as if were your keys in order to encrypt stuff, right? Once What is a key? Well, a key can be used in any one of your more common block ciphers and that sort of thing, correct? And then you can use it just fine as if and to share information across computers. Because that's normally what we are dealing here, right? Normally, the middleman sitting in your communication and picking up things that can interfere. Now, what's the takeaway of ECC? Well, ECC normally, what it does is reduce the number of bits as the way we start this conversation, right? It's the computational size of the numbers involved. They don't need to be as large as those involved in RSA. But even, and this brings us back to earlier definition of what makes some cipher secure. And we normally agree that is the size of the key. Is that correct? Because then brute force will take, a long time in order for someone to break that key, correct? So, well, guess what? Even though these elliptic curves encryptions don't have as large numbers, they are still very strong cyber systems. Yeah, so here it says that it's 10 times smaller, those numbers, right, than those given by RSA modulus. Isn't that cool? Like the difference between all these crypto systems, but I guess the gist of it is behind the math, right? You cannot understand why we use ECC versus RSA versus Diffie-Hellman if you are not aware of the math. And that's what we do here. Sorry that I had to walk through the math on this chapter because, like I said, the next chapters are a little bit less intense. Well, it's still the next one regarding hashing has a little bit of math, but I think it's simpler than this geometric math. All right. What time is it? So we can take our hourly break. Why it's wrong here? It says it's 9:41. What time is it? Oh, my clock here is messed up actually. All right. Let's have a break of 5 minutes and we'll be back. We'll resume in that much time. 6:57, we'll be back at 7. Oh, it's 7 actually. 7:05. Pause hashing. Why it's asking again that this what? My pointer is hiding behind this. What?